My name is Andy Shearer. I'm the exact opposite of the model of a scientist which the university wants to portray. I'm a white, older male scientist. I can't do anything about any of those aspects, so you're stuck with me. I'm an astronomer. I heard Jasmine talking about astronomy and stars earlier on, so I'm going to actually take that thread and I want to talk about the kind of stars which I look at, which are neutron stars. Jasmine talked about how big all the stars are which people see out in the firmament. Stars I look at are small. A neutron star would fit into Galway Bay. And what I want to try and do is talk about neutron stars. I want to talk about why physicists look at them. I also want to talk about what a physicist is and what we do. And you'll find out by the end of it, all a physicist does is talk about common sense and gives it a long word to make them seem extremely clever. So what I'm going to be talking about at some point later on is something called angular momentum and the conservation thereof. And for that, I've got a prop, which your feet are on. Which I shall use. So I'll be looking for a kind of someone to help me with this, who's quite small and quite near. Okay, neutron stars, what are they? The pulsars is the way we look at them. They turn around and they give a flash of light every now and again, every time they spin round. They spin round very quickly. They're the end of a star's life. Most of you will look at the sun and think, well, that's good, it's going to be there tomorrow. It'll be there for the next 5, maybe a little bit more billion years. If it was so it's fine, it's going to be around. If it was a slightly bigger star, if it was about 10 times bigger, it wouldn't last for 10 billion years, it would last for about 20 million years. And it would then be glowing very hot, much hotter than we could actually survive. It would then do what the sun does for about that amount of time, burning hydrogen into helium, which is great. After about that amount of time, it'll run out of fuel, and it will collapse a little bit. And in collapsing, it does two things. It'll start to spin slightly faster, and it will get slightly hotter, and then it will start to burn helium into carbon. And then it will run out of helium, and it will collapse and spin a bit faster, and it will carry on doing this until it gets to burning rock. And it'll be at about a temperature of about several billion degrees. Any physicist would then say, is that centigrade or Kelvin? It doesn't really matter. We will then be at several billion degrees. The star will have now shrunk to the size of the Earth and be made of rock and create iron. And at that point, the power of the sun with fusion would then stop like that. It stops in about a quarter of a second. The star then collapses, and you get an enormous explosion called a supernova explosion. And at the bottom of it, spinning around very, very quickly, is this neutron star, which is about 1.5 times the mass of the sun, but composed about 30 kilometers across, would fit into Galway Bay. It's an enormous amount of energy. And they spin about once every 10 seconds for the slow ones, 30 times a second for the fast ones, the ones I look at called the crab, up to 700 times a second. And to give an idea of those kind of speeds, I want to take the analogy of a washing machine and a cat. Some of you might see where this is going. At once every 10 seconds, you could put your cat into the washing machine with your washing, and what would happen is the cat would be well exercised at the end of it, because it's trying to keep up, and the washing would be wet. If it was going once a second, the cat would survive, the washing would be wet, but when you open that door, you're going to have a seriously angry cat, which is going to come up. If you then run it at 30 times a second, the crab pulsar, the one we study, that is spinning around at, if everyone's got a really expensive washing machine, 1,200 revolutions per minute is good. This is 1,800 revolutions per minute. And this is 1,800 revolutions per minute. It's 20 kilometers across, and it weighs 1.5 times the mass of the sun. For those people, that's about 10 to the 30 kilograms. That's the science bit. That would then kill the cat. It would be weighing about 300 times its standard weight at that point. That's not good. But your clothes would be lovely and dry, and but you would have a dead cat like that. The fastest one is about 700 times a second, and that's a rev speed of 42,000 RPM. If you put your clothes and your cat into that, at the end of it, you wouldn't have any clothes, because the clothes would kind of disassociate into all the little fibers and everything else like that. Sadly, so would the cat. So you'd have this rather mess of kind of glunk coming out. So that's the kind of speeds you're talking about with these strange stars called neutron stars and pulsars. But to actually show why they speed up, this is where I'm going to do a prop, if I have time to do that prop. Can you do us a favour? Can you pass? There's 2 weights and a big block. That's the easy bit. I told you it was heavy. Why do you think I didn't want to pick it up? Okay, I now need a volunteer. Ken. Changed my mind. I think you know what's going to happen. Oops.
General idea, yeah.
Okay, can you stand on that? Ken's from the School of Physics. So I'm going to get out of the way.
Thanks.
So, excuse me, I'm now going to leave. Get it one in each hand and out. And I want you to do some method acting at this point. I want you to pretend to be the central core of a star, spinning around about once a day. And now I want you to gently collapse down to a neutron star. And you speed up when you collapse down and you move out when you don't. And that is kind of common sense. People know that kind of vaguely happens. Apart from Ken, you now feel sick. That's all right. Thank you, Ken. I think Ken needs it. I think I'm Ken's internal examiner for his PhD. I think you've just passed. That's conservation of angular momentum. And all that's happening he was changing his shape. And there's no motor on there or anything else like that. And that's why pulsars speed up the way they do. All the mass, which used to be kind of spread out over millions of kilometers, now condenses itself down into about 10 kilometers. And consequently, Ken sped up in exactly the same way as a neutron star would speed up. And in some ways, that's the reason why I'm a physicist. Because I like the idea of things spinning around here are obeying the same physical laws here, in Tune, in Dublin, on neutron stars, on planets, and wherever they happen to be, the same physical laws apply. So I like that kind of unity across the universe, let alone across the world. It's the unity across the universe, which is important. And with that, I'm going to run away. Thank you.
Andy Shearer, everybody.